I know that you're having a good time, but you can continue after lunch. Thank you everyone for joining. We just heard an excellent ITC colloquium by Yuri Levin that came all the way from New York City, where you have the second best restaurants of every nation. We'll hear first from our own Karin Oberg, who will tell us about why Jupiter probably.
I know, her Rachel just complaining about not being confident.
Well, it's okay. In science, we're always uncertain. Probably originated in the outer solar system. Then we'll continue with Evgenya Shkolnik from Arizona State University. Where she is. And she's giving the CFA colloquium later. But at this lunch, she will talk about measuring the magnetic fields of giant exoplanets. And then we'll hear again from Yuri, who will tell us about negative dynamical friction on black holes. So actually, it's not friction, it's acceleration. And finally, we'll hear from Shantanu Basu over there, who will tell us about the mass and luminosity function of supermassive black holes in the direct collapse scenario. Karin.
Thank you. Okay, so Jupiter. Hopefully, you all remember, roughly where it sits in the solar system, around 5 AU. But the question is, did it form there? And we care about this because it probably matters quite a bit whether a planetary system ends up with a gas giant or not, and where it ends up. If you have a gas giant that ends up very close to the star, it might kill off any potentially habitable planets that you were sort of, sweeping through. And it might also be that having a Jupiter that's sitting outside of the water snow line, so where water goes from being mainly in the gas to being mainly in the ice, that actually has some protection, provides some protection or starvation of the inner solar system, resulting in rocky planets forming instead of sort of mini Neptunes. So understanding Jupiter's formation and early movements is important for understanding of how planetary systems are sculpted. So since Jupiter is sitting around 5 AU, it's, I think, by sort of commonsensical to think that it formed roughly around 5 AU. About a few years ago, there was a model that took into account that had Jupiter formed through pebble accretion. I'll come back to that. Would actually wanted to put the formation a bit further out, sort of to 10 to 15 AU. And now where Robin Wordsworth and I want to push it is out to 30, 40 AU. And I'll try to convince you why this actually is very reasonable. And what we're going to argue is that Jupiter's composition, together what we understand about the composition of our solar nebula, together is what pushes the formation out this far. So one of the most important things that sets the composition of a disk like our solar nebula are the sequence of condensation lines as you go through the disk. So different species have different volatilities, and therefore will transition from being mainly in the gas phase to being mainly in a solid at different distances from the star, just because of the lower temperatures that go further and further away from the star. So for any species, we can estimate that based on laboratory measurements of when a species should condense. And in a few instances, we can also observe these snow lines in analogs to our solar nebula. So this shows the first observation of the CO snow line around another sort of sun-like star, and we can use the theoretical laboratory information together with these observations of snow lines around other stars to estimate where these snow lines should have been in our solar nebula. So that's what's sort of our estimates of the most important volatiles in any disk, including our disk. Their snow lines are plotted here. So what you see in the thinner, darker lines are the abundances of species like water, CO, CO2, N2, ammonia in the gas phase. And then when something in the gas phase goes away, it's because it's freezing out onto a grain. So you see the solid phase going up. Now, I already said how we figure out where snow lines are. But the second thing that's as important is to know which snow lines matter. And that's determined by chemistry, by what are the main carriers of oxygen, carbon, nitrogen, sulfur, phosphorus, and things like noble gases. We know what the carriers are because they don't participate in chemistry. So for oxygen, most important things are things like water, CO2, carbon, CO2, nitrogen, it's mainly an N2, but with some ammonia, and so on. So what we can do then is we can estimate what the elemental composition in the gas and the solids are across the solar nebula. So that's what's shown here for normalized to sulfur. And the reason I've normalized to sulfur is that sulfur seems to always be in the solid where we care about it. So we know where the sulfur is. So what's shown here is where what the elemental abundances are in the grains for oxygen, carbon, and nitrogen, and then in the gas would just be the inverse of that. So importantly, and the thing to keep in mind, what was shown here is in the sort of faint yellow, this is 5 AU, so this is where Jupiter is sitting today. Now where I want Jupiter to be, what I think Jupiter is forming is out here beyond 30, 40 AU. So if you look at the elemental compositions in the solids, you'll see at 5 AU, they're very different for nitrogen, carbon, and oxygen. While out beyond the furthest snow line, which would be that of N2 or argon, dependent on which measurement to use, everything is unity. And that's just because everything is frozen out. It's kind of a trivial result. Okay, so that's the background info. So now, what about Jupiter? So this is the nebular composition. So what about Jupiter's composition? So Jupiter has a very odd composition. So if you look at the elemental composition of Jupiter, it looks like this when we have it with respect to solar. So think about this as, for example, the oxygen over hydrogen in Jupiter compared to the solar oxygen to hydrogen. That's what's shown here. So we're going to forget about the oxygen for the moment, because that's probably a measurement problem rather than, and we'll come back to why it probably is, and there's a new mission that's going to fix that. And look at everything else. And what you see is that all the other elements are enriched to the same degree. So solar, if everything was solar, it would be on the red line here. And we see that everything is enriched by about a factor of 2 above that, so that they have, they're at 3, right? So they have a sort of extra factor of 2. So why is this strange? Well, it's strange if we think about how giant planets form, and therefore how we could get any enrichment at all. So a gas giant planet, we think most of them form, including Jupiter, by first forming a solid core. And then once that one gets to sort of 10 to 20 Earth masses, you accrete an envelope of gas from the nebula. And that one is going to be solar composition or less. So that one would be below that red line. And then you pollute that envelope with solids, either leaking out of the solid core or incoming comets and asteroids. And that's how you get above that solar composition line. Now the problem is, and why this is so odd that Jupiter has this constant enrichment pattern, is that if we look at what the solids look like, the polluting solids, where Jupiter is forming based on these successive snow lines, you might remember from the last slide, that there you did not have a solar composition. You had the nitrogen compared to sulfur was very low, the carbon to sulfur was fairly low, and even the oxygen compared to solar was somewhat depleted. So it's really difficult to get this constant enrichment pattern from 5 AU solids. On the other hand, it's really easy to get that enrichment pattern from, let's see if this one, it might have frozen, maybe? Okay, working again. It's really easy to get this enrichment pattern if you have solids out at 40 AU, because there everything is frozen out. So there you will actually get something approximately that is this constant enrichment factor. So the scenario that we imagine to explain then this constant enrichment in Jupiter is that you have the core formation out at 40 AU. Then as the envelope starts accreting, you migrate inward, and then you get somewhat polluted by planetesimals at 5 AU. But the main enrichment of these heavy elements into the atmosphere comes from the core dissolving into the envelope. And if you do that, you get something that agrees very well with observations, except for oxygen. As I said, we'll come back to that. So there are two major things that needs to be possible for this to be plausible. One is this large-scale migration, and the second is that the core dissolves. So let's start with the large-scale migration. It's actually been, as I said, a few years ago, the reason people started pushing Jupiter's formation a bit further out is that if you start forming a gas giant and then accrete very quickly and then accrete a gaseous envelope, you start exchanging angular momentum with the disk and migrate inward very quickly. So actually in their model, they had to have Jupiter's formation start out at 15 AU in their fiducial model to end up at 5 AU. But they actually had to do a trick to only be at 15 AU, which is that they started at 2 million years. They said no planet formation before 2 million years. And this is not obvious that this fits with observations. So this is HL tau, a very young disk, less than 1 million years, already has a lot of structure. So I think we have some observational evidence, like there are other ways you could get that structure, but I would say the observations are pointing towards that planet formation starts before 1 million years. And then their model, if you dig into sort of their last figure, actually has some Jupiter forming out at 30 to 40 AU. So what about core? And furthermore, if we look more outside of our solar system, disks around other stars, we do see a lot of things going on far away from the star in terms of structure. And simplest explanation for this is that planet formation has begun out there. So it's the final thing I want to say is that the core, so we can migrate, that's probably not going to be a problem. How about core dissolution? How likely is that? Very conveniently, about a month ago, this paper was published, which tries to explain why Jupiter seems to have a fluffier core than expected. And their idea is that you had a giant impact that sort of went all the way into the core and then dispersed the core material into the envelope. So also core dissolution seems to actually to be plausible. So I think there's several reasons to think that this happened. It's very difficult to explain Jupiter's composition any other way. But there is a measurement we're going to need to show that we're right. And that's that pesky oxygen that's down very low according to the old Galileo measurements. Juno should be able to give us a measurement for that. Hopefully that will be out in a few months, and hopefully it will put us right here. So that's prediction number one, should happen soon. And the other thing is that Saturn should look similar to Jupiter in terms of having a fairly flat enrichment pattern, which is going to require sending something into Saturn, which may or may not happen in my lifetime, but at least theoretically, that's also testable. So thank you.
That's why exoplanets were not discovered for so long. Only when some people dared to look at hot Jupiters, they found them. Now, you are saying that not only they were wrong about not having migration, but actually our own Jupiter was not born where it is. So the fact that we understand where Jupiter is incorrect. And now the question is, why did it park at the location where it is? Do you have any conjecture?
In these models, the reason that the planet stops is basically that you run out of gas to accrete. So whether you go all the way into the sun and becomes a hot Jupiter or park somewhere further out depends on how far out you started and how much gas, how efficiently you sweep up gas. So what I think we should expect to see is actually a range of, if this model is correct, we should see a range of positions where you have a gas giant.
In almost any planet migration model, and there's a lot that say a lot of things, but on almost any model, the time scale to get from 30 AU to 5 AU is much longer than the time scale to migrate in from 5 AU to crash into the center. So it seems like you have to be pretty fine-tuned to like have the disk suddenly disappear right when you hit 5 AU. Is that a problem, or is it?
So I don't know if it's a problem. I think it depends on how many Jupiters you find around 5 AU, right? So we don't yet know that. The one thing that I think we don't know, and which maybe leads that you should expect some buildup around, let's say, 2 to 5 AU, is that maybe when you have the water snow line, it's not that it causes Jupiters to form, but it might cause some discontinuity there, which might help to stop planets. But otherwise, I would say it would not be strange to have many of them, like many more, continuing all the way than to park at 5 AU, dependent on what happens there.
So I was just wondering, we know outside past Neptune, there's a lot of weird things that make people think Planet 9 might be out there. Would Jupiter migrating maybe give any of these effects as well?
I have no idea. Would I guess be the short answer. The slightly longer one is that if we think it's plausible that you form something like a 20 Earth mass Jupiter core out at 40, 50 AU, it seems to make it slightly less implausible to form other big things and then maybe kick them outwards instead of having them migrate inwards if they formed a bit later.
I mean, related to that, there's a lot of dynamical structure out beyond Neptune that is evidence of an outward migration.
Yep.
How would you fit this together?
Well, so my understanding is that that kind of outward migration happened as sort of once Jupiter was already fully formed. Whether you start forming Jupiter at 3 AU, do a little U-turn, and then and then lock it into place, or you have it sort of migrate all the way and do that, sort of lock it into place with Saturn and kick out. That seems to be a separate issue in time, as far as I understand.
But Karin, your argument about having the solids holds also for farther away, right? So why not push it even farther?
So I think what you would want to say is that Saturn, because it has such a big gas mass, can't have started forming too much later than Jupiter, and therefore should have gone through the same kind of thing. Neptune and Uranus, you might be, there I think it's less clear because they didn't accrete that much gas, so they might have started to form a bit later, in which case they would be allowed to form sort of further in, or even if they form through the same mechanism. So I think there's just, the model predictions are less clear, but it definitely doesn't rule out that they started forming further out.
Yeah, but my question was, why didn't Jupiter? You could have started Jupiter farther out than you assumed in your modeling, right?
Well, so it becomes a question of timescales, and unfortunately we don't know exactly what our nebula looks like. If you make the nebula more massive, you can push it even further out.
Any other questions, Karin?
I'm up here.
Oh, there. I was like, I hear you. I recognize the voice.
It seems just if the only data point that doesn't fit a scenario is being remeasured. So there's two questions. Why don't you believe the oxygen, and will the other elements also be remeasured?
Yeah. So the nitrogen has already been remeasured and fit the previous. So the new measurement, so it's not just that we are redoing the same thing, in which case it would be bad. Juno is going much deeper into Jupiter than Galileo did. So it should give better measurements on the bulk composition. So the worry about Galileo was that because it didn't go very deep in, this very low oxygen measurement is due to sort of superficial inhomogeneities in the upper layers, especially when it comes to water. So that the deeper in you go, the better that should be. That being said, I would love to see measurements of Saturn. I mean, I think that would be very good. And of course, exoplanets is the other big thing that those measurements.
Oxygen stays that the way it is now. What will you measure?
Well, the nice thing is that no other model can explain that oxygen as well, while sort of perturbation of my model actually can. But that's another paper. But I think the really strongest one is to see the same kind of pattern in Saturn. But the competing model to explain this in Jupiter has an oxygen enhancement of 7 to 10. So it actually, so that's the big difference in the predictions. Oh, yeah. Okay. Thank you. Very nice. Thanks. All right. It's quite a room. You guys are spoiled here. Well, we're going to continue the theme with giant planets. So if you don't love them yet, get on board. Okay. Let's start the show. Okay. There we go. Okay, so I'm Evgenya Shkolnik. I'm a professor at Arizona State University. Also giving the colloquium this afternoon on something totally unrelated to this. So we can talk. So this is my opportunity to talk about one of my favorite fields, which is measuring the magnetic fields of giant exoplanets. So thank you for that. In fact, when I gave the colloquium here 10 years ago, it was on this subject. So this is a tiny update on what I presented back then. And in that decade, I have to say that magnetic fields on giant planets has not become mainstream in our field yet, which is a little disappointing, but we're working on that. But it has been has been thought about for decades, long before exoplanets were actually even discovered, and even before I was born. Here are some of the earliest papers that discuss the searches for exoplanets by looking for radio emission from the planet's magnetic field, right? Because Jupiter had this nice strong magnetic field, bright radio emission. And so this was the way people had, not originally, in one of the first couple of ways people were looking for exoplanets long ago. And if anyone is interested, this particular reference was hard to find. It was sent to me by Jeff Bryden at JPL. It's 5 pages and super interesting and tells us exactly why it's going to be really, really hard to find radio emission from Jupiter's. But I think we're just around the corner on that front, and I'll talk more a bit about that. But my interest in exoplanet magnetic fields came from not planet hunting, but rather planet characterization. So we wanted to know about the interiors of these planets, and magnetic fields is what tells us about the interior dynamics. So for instance, Earth's magnetic field is generated by its liquid nickel-iron outer core. We hypothesized that Jupiter's main constituent is metallic hydrogen by the detection of its magnetic field. But in addition to the magnetic field probing the planet's interior, it also gives us information about the planet's exterior. So for those of us interested in planetary atmosphere evolution and whether the survivability of the planet's atmosphere is important, say, for Earth-like planets around inhabitable zones of active stars, we might really want to start thinking more deeply about magnetic fields in general, especially about smaller planets. And here's just a picture from MAVEN. MAVEN is now studying Mars, but is going to try and tell us, I think, one of its goals is how important is the magnetic field of a terrestrial planet to the survivability of its atmosphere and therefore its habitability. Okay? But the way we've been doing it is something we call magnetic star-planet interactions. And what that is, that was first hypothesized by Kunz et al. In 2000, just around the time that I started my PhD, so it was very convenient for me. And what they thought was, okay, if you have, because at that time, right, we pretty much only knew about hot Jupiters. And if you take a planet and you take you take a star and you take the hot Jupiter, that's about 10 stellar radii away, you're actually sweeping within the Alphane radius of its central star. And if both the star and the planet have magnetic fields, then some interaction might happen. It would manifest itself as a hot spot on the star that is modulated by the planet's orbit and not by the stellar rotation. So that's a key signature, and I'm going to show you the data that shows this. That
it goes with the planet and not with just the star, stellar rotation. And then in more recent work since then, Nuccio Lanza, one of my favorite collaborators, came up with some relationships to explain what this phenomenon might look like. He explored flux tubes, he explored magnetic reconnection, and now there's some other teams also working on this and doing 3D MHD models in order to explain the possible magnetic interactions between a hot Jupiter and its central star. So in a simplified version, the SPI power, so the star-planet interaction power emitted, so that's a measurable quantity, that's what we measure, right, is related to the stellar magnetic field strength, the planetary magnetic field strength, and the relative velocity between the fields, the flow of the planet's motion around the star. Now, all of these are now measurable, right? We know this. We measured this. We spent some time doing Zeeman Doppler imaging to measure the stellar magnetic fields, and we can measure the power through this interaction. So to go back kind of to historical days, this is from my very, very first paper, when we tried to do this for HD 179949. This is a hot Jupiter looking at the calcium K emission of its parent star in very high signal-to-noise and high-resolution data from the Canada-France-Hawaii telescope. And what you see is that the emission core varies a little bit there. And when you look at the residuals, it's a whopping signal, right? It's pretty high signal-to-noise data. And then you integrate this, the residuals, and you can plot it against the orbital phase of the planet. And you see that it does vary with the orbital period, which in this case is 4.3 days, and not with the stellar rotation, which is roughly 12 days. And this has been, we've repeated this, we've seen this before, other teams have seen this, and it feels like a pretty strong result. So we've been continuing to do this, and we've done this for a few stars. And this new paper came out by a postdoc who was in my group, Wilson Colley. Now he's a postdoc at CU Boulder. But he has taken all of our old data and has done two new innovations to really try and get at the magnetic fields. One is he did a very, very careful, accurate flux calibration of the Echelle spectra, which those of you who work in that space know that that's its own challenge. And in the meantime, in the decade since I last visited you, we've been working on measuring these magnetic fields with spectropolarimeters. So now we have all the things that we need in order to fit it into the model, and we get these numbers. Okay, so we get what we call semi-empirical magnetic field strengths. They tend to be larger than Jupiter's, so 20 to 120 Gauss. These are the 4 hot Jupiters that we've been able to do this for thus far. And in this paper, we plot the polar field strength against this paper by Yadav and Thorngren. Is Rakesh here? Because he could tell us all about it. He's here at CFA. And so what this plot shows you is we're kind of validating their models where they have this internal heat flux because of the central star. So that because these planets are so close to the star, it's dumping in even more energy, and you have this increased internal heat. The point of this paper was to try and explain the puffiness of the hot Jupiters, but at the same time, you can also expect stronger fields with this same idea. Okay? So the next step that we're trying to do, because we're trying to get at the magnetic fields of all of this, is to understand it now from the other side. So here we are looking at Jupiter. Here's our results here, Colley et al. 2019. And it's plotted on a scaling relationship between magnetic energy density with some quantity that's proportional to the convective energy flux. And here, it's these ones that I want to point out to you now. These are the brown dwarfs that Melody Cow is studying. Melody Cow is a Hubble Fellow with me at ASU, and she is looking at the radio emission from brown dwarfs. And the reason why I had initially hired her before she won her Hubble, I initially hired her as a postdoc because I want to understand these fields, and I don't understand how isolated brown dwarfs have kilogauss fields. So here we're talking, these ones, right, have 20 to 100, say, Gauss fields. And those ones are greater than that at kilogauss fields, and I don't really know how. Maybe people in the room understand how these could be generated. It's certainly not a heat flux issue from any external source because they're not next to bright stars like the hot Jupiters are. But we have a whole program to look at the young brown dwarfs, because one thing that is very interesting to me about young brown dwarfs is that their planetary mass. Okay, so young brown dwarfs can be 10, 13 or so Jupiter masses, which means we are now with radio starting to measure magnetic field strengths of Jupiters, right, even though they're technically brown dwarfs. And they're isolated, right, so their formation process was probably very different. So to conclude, I want to point you to a relatively recent and now completely outdated review that I and Joe Lama wrote for the Handbook on Exoplanets on Magnetic Star-Planet Interactions. But kind of more importantly, I really want you guys also to keep an eye on the future, because I think that magnetic fields are really just around the corner to be a ubiquitous observation. So you guys have Antonia here. I don't know if she's here today, but I know she talked to you guys. There she is. Thank you. She talked to you guys last month about her method of detecting magnetic fields using the spectropolarimetric signal of helium-10-830, which I think is very exciting. There's, of course, the decades-long search in radio, and as we get to lower and lower frequencies, like with LOFAR, I think really within a year we should be getting some convincing results of hot Jupiter magnetic fields. I think for Earth's, though, we'll have to go into space, and there's a lot of talk of building, say, small satellite arrays in space or on the far side of the moon in order to do this, and that's not crazy, and I think will happen in our lifetimes. And Melody Cow is certainly continuing her search in the radio of the brown dwarfs, pushing to smaller and smaller masses. So thank you.
Presumably there are interesting cycles, just like the star has cycles. Also the planet has a different period, perhaps.
Right.
So you would expect changes over time in the way that the two relate to each other.
Between the star and the planet? Yeah, and we do, in fact. We've been monitoring some systems a lot, and you can see the stellar field changing. So you see activity cycles. So on Tau Boo, because we've been banging away on it so much, we see the magnetic pole reversal multiple times on a 1-year time scale, and that should change too because the stellar field is changing. How the planet, so we've been thinking about how the stellar field changing affects our observations a lot. I have not thought at all deeply about how the planetary pole reversals would change. So thanks for the extra variable. We'll have to think more about that. It should be interesting. Hopefully it's not changing on the time scales of our observations. Right. So let's hope. The star's already causing trouble as it is.
Questions or comments? If not, we are all looking forward to your development. Thank you.
Sure.
Here, I'll plug you in while you get your.
Thanks, Paul.
Right, so Avi was right in saying that I'm going to talk about accelerating black holes. So I'm going to talk about accelerating black holes in two contexts. One context is gas dynamics, and this is very speculative. It's just an idea, a sketch. But if it's right, it may be applicable to some parts of common envelope and also to compact objects which are embedded inside AGN accretion disks, compact objects like stellar mass black holes or neutron stars. And the second part is to do with not so speculative experiments that Anne-Marie Madigan and I did several years ago on stellar dynamics, but I'm still thinking about these experiments. So if I have time, I'll talk about them as well. So first of all, about black holes moving through gas. If you go into a frame of reference of a black hole, there is a classical Bondi-Hoyle solution, which you see on the left-hand side. So the way it looks like, I think I have a pointer. Okay, the way it looks like is that the material which I'm not sure if it will add a lot. Okay, so in the frame of reference of a black hole, this is a conceptual figure. It's not a simulation or anything. So you have the gas which comes in, converges under the action of gravity of a black hole. There is a bow shock which connects the near vicinity of a black hole with the rest of the flow. The gas concentrates in an overdensity behind the black hole, and black hole accretes from this overdensity. So this is a classical Bondi-Hoyle solution. And you can see that if you're thinking about the gravitational influence of this perturbed gas, then the gas is going to pull backwards on a black hole. So this is a normal dynamical friction that has been worked on by many people. Now, imagine now that instead of forget about the black hole for a second and just think about the object which has very strong outflow for whatever reason. We'll talk about reasons later on. This outflow will create, if it's sufficiently strong, it will create a much wider bow shock than in the previous figure. And so there will be the material which will hit this bow shock will flow around this underdense region. And of course, the gravity is going to pull forward. So this is an acceleration. And you can calculate this. And we did. This is the honest calculation in the paper that I wrote with Andrei Gruzinov and Chris Matzner, where we took Wilkins' solution from 96. So Wilkin considered he actually miraculously found an analytical solution for the density structure of this bow shock, but in a very strange approximation, in an approximation where you're basically considering zero temperature. It's an isothermal zero temperature gas, so it's a completely sticky collision, but it conserves momentum. Okay, so in this approximation, he found the density structure analytically of this bow shock, and then we could integrate this and get the force, and the solution after this integration is as follows. So if you take this wind and you compare this wind with the velocity of this object relative to the ambient gas, once the wind velocity exceeds something like half of this velocity of this object, then the gravitational influence of this perturbed gas is going to exert accelerating force. So the object is going to accelerate. This result is exact, or at least it's true. So since our publication, a student, Xinyu Li, working together with Phil Chang, has done a simulation of this particular setup, but with more reasonable equation of state. And the simulation beautifully reproduces the qualitative features of this result. So once outflow velocity exceeds some critical value, indeed the friction, the gravitational influence of perturbed gas reverses direction, propels you forward. Now, do black holes have outflows, accreting black holes? Well, first of all, let me ask a question. When can this be important in nature? This can be important in nature only if you have quite dense gas, right? Because you want this effect to operate, quite effectively. If you have dense gas, then you're going to have quite a high accretion rate onto the black hole. So this is called, once the accretion rate exceeds Eddington, this is the so-called supercritical accretion rate. Now I have to go back to the classic paper by Shko and Sunyaev, who in 1973 were asking a question, what happens if you take Schwarzschild black hole, or Kerr black hole, whatever, some exact solution of general relativity, and how will it look like to observers? Okay, this was the fundamental question they were asking. And of course, there could be a variety of circumstances, and I think they were smart enough, if you read this paper, they've considered a wide range of possibilities. And one possibility that they've considered in some detail is the supercritical accretion. And so, for example, they say that in the supercritical accretion, they're predicting that most of the material you're trying to accrete to the black hole will come as an outflow. Okay, so they make an estimate of velocity of this outflow and the density of this outflow, and make a prediction that such a black hole should appear as an optical star with weird colors and lines. Okay, this is the prediction of their paper, which I think is here. So may appear as a bright hot optical star with strong outflow of matter. So this is 1973. And in 1976, a microquasar SS433 was found first in this paper, identified in the survey of weird stars in the galaxy. Okay, so this is, a beautiful confirmation to my mind of the prediction that was made in Shakur and Sunyaev's paper. Okay, now what do we know about SS433? We know that roughly speaking, the estimates that were made in Shakur and Sunyaev's paper are correct. The estimates for the mass of the wind, the velocity of the wind. So all of this seems to be consistent for SS433 with the simple, I would say somewhat simple-minded prescriptions in Shakur and Sunyaev's papers. But do we know much more? The simulations by Oleg Sadovsky and Jan Feish-Young, they're working very hard, but to make this type of predictions for the properties of the wind requires very large range of the simulations, and I don't think we are quite there to do it from the first principles. Maybe I'm wrong about that. So what we have tried to do is to now synthesize this into some kind of cartoon consistent picture where you have a black hole sitting here, which is being fed by part of this inflow, and this part of this inflow goes into the disk, and it comes out as this supercritical wind. The wind creates a bow shock in the rest of the material, and so we calculate various regimes, and we find that for simple prescriptions taken from Shakur and Sunyaev, for some density regimes, which are given here in this corner, you can get an accelerating black hole. Okay, and if we are correct, then this is astrophysically significant in a variety of contexts. So I'm not going to talk about all the contexts. You have people here, Morgan and Selma, working on common envelopes. So I won't say anything about common envelopes. I'll talk about something which is personal to me, which is a scenario that I have proposed some time ago for stellar mass black holes sitting inside AGN accretion disks, right? And so what I have argued is that these stellar mass black holes will experience drag from the gas and migrate inwards and merge with a supermassive black hole, predicting extreme mass ratio in spirals. Okay, so this is a very speculative paper, or two papers that I wrote some time ago. So since then, Barry McKernan and colleagues have argued that if these black holes find each other in these disks, this could also be an interesting LIGO source. Now, the reason I'm telling you this is that I'm worried that this scenario is wrong, and that the black holes will actually migrate outwards and not inwards because of this effect. If you have outflows, and I have to say that these black holes, when they're sitting in the disk, they have to accrete at super Eddington rate. So if this happens, they'll have massive outflows, and how these outflows will interact with the accretion disk, I don't know. But I'm worried that they'll migrate outwards. Do I have time, Avi? Yes. How much? 6 seconds. 6 seconds. Maybe I should stop here and take, if it's 6 seconds, I will stop here and take questions.
Yuri, there is one other context that you didn't mention, and that's Basu, that has a very fast wind actually into its environment. And so if a neutron star, magnetized neutron star, is born in a supernova remnant, then you might, if there is some material around, you might propel it away from the center.
Mm-hmm. That's a very interesting point. Now, I don't know if supernova remnant itself is dense enough. This should be estimated this afternoon. When we put this paper on the archive, so just to second your comment, or maybe kind of look at a different angle, as this paper appeared on the archive, we had a long letter from Chris Thompson saying that he thinks that this is the type of effect which gives pulsar kicks. So this is not quite the supernova remnant, but it's a supernova explosion itself, where the neutron star is kind of born, but it also has a kind of outflow. And so from Thomson's point of view, he argues that it's this kind of effect that is, if you move the pulsar in some direction, then there is some underdensity behind it, and this propels it and gives it a kick. And he has published similar things, not worded in quite this way, but he has published similar things, like 15 years ago or so. Very difficult.
So maybe I didn't understand your argument totally, but of course, this effect requires a relative velocity between the gas and the black hole. But if you're in a disk, the black hole's co-orbiting with the gas.
Right.
So why does this affect migration in a disk?
Yes. So I should give some. So like Avi says, it's difficult to be original. So I should give some credit. I should give a lot of credit actually to these people. Hold on a second. This ones. Massé, Frédéric Massé and his group in Mexico. So they've found that they came at it in a completely different context, and this wasn't to do with outflows, but it was to do with just hot planetesimals in protoplanetary disks. And they found that these hot planetesimals, because of thermal effects, potential thermal effects, so this bubble is created thermally, that they see both, like if they put these planetesimals in homogeneous medium, they see acceleration. And if they put these planetesimals in the disk, then they see a reversal of the torque, and these planetesimals migrate out. So it's not quite, how can I say? It's not quite exactly this, but it's the fact that if you have outflows, it alters the surrounding area. So it's not quite literally this particular thing, but I'm worried that something similar will happen in the disk if you have outflows that will sufficiently alter the surrounding.
Migration is very sensitive to the details. So
right.
You can definitely imagine that kind of thing.
So, in the sense of this with a black hole and a common envelope, or plunging into a common envelope, do you expect that this will kind of grazing that you would get from this negative dynamical fraction happen only once, or you would get like this continuous falling in and falling outwards? And then the immediate kind of follow-up question is, do you make any predictions of what, if you manage to get the black hole deeper into the envelope, would you just make any predictions on what it would look like? Would you see like a jet coming out of the envelope, or would it never reach the surface, or?
I won't make any predictions. This is a cartoon. It's a child's drawing with some numbers, right? One needs some simulations. One needs to do some simulations in order to make solid predictions. I want to answer your question in this way. SS433 has been around for 40 years, and the orbital period of SS433, which is accreting at the rate of 10 to the minus 4 solar masses per year, has not changed.
Okay, well, let's think.
Yeah. I fixed that.
There we go.
Okay, thank you. I'm Shantanu Basu. I'm from Western University in Canada. I normally work in star formation, but I'll be talking about some new projects where we're cross-fertilizing into an area you know very well, I'm sure. So I'll be talking about some predictions we can make about the distribution of supermassive black hole masses and perhaps luminosities based on some very simple ideas that exist about how they form and grow. Now, one of the big challenges in recent cosmology, as you may know, is that the very high mass quasars that are being observed at redshift 6, 7 are already in place at within 6, 7, or 700, 800 million years after the Big Bang, but they've grown to about 1 billion solar masses. So if you take this idea of Eddington limited accretion and take these three most massive early universe black holes from Benadas, Mortlock, and Wu, those are these three data points in mass, and then run them backward according to Eddington limited growth, then you'll notice that if you want them to form, say, at redshift 20, their initial mass would have been more than 10 to the 4 solar masses. So that's the basic issue with these observations. You need starting masses that would be much greater than POP3 remnants, stellar mass black holes, and or you may need super Eddington accretion, or God forbid, even hyper Eddington accretion. So this is one of the conundrums with standard Big Bang model, let's say. And so to look at a schematic version of the previous figure, you can say that stellar remnants, POP3, may be up to 100 solar masses, and they typically will photoevaporate most of the material around them after they reach that mass. So they not only have a hard time growing initially, but even if at a later time they come into contact with large amounts of gas, they'd have to grow at really a hyper Eddington rate to get to the observed masses. On the other hand, you can jumpstart by having something of order 10 to the 5 solar mass initial object, and then you could perhaps get to the observed quasars in at least close to Eddington limited or close to Eddington accretion rate. So this is, of course, the issue that Avi has promoted, and Avi and Volker Brahm wrote a paper many years ago where they were talking about the Lyman-Werner flux leading to dissociation of H2, which would allow collapse of very large objects. I'll talk more about that later, but just for preliminaries, if you have Eddington limited accretion, the nice thing is you have this beautiful exponential growth formula for the mass, where the growth time is related to the Eddington time. The Eddington time itself is all coming out of fundamental constants, and it's 450 million years. And if you make some assumptions about the radiative efficiency being about 1/10, you have this correction factor here, and your Eddington factor, typically you'd take that to be 1, but if you want super Eddington accretion, you can set chi greater than 1. But if you take the typical values for these two numbers, you'll get about a 50 million year growth time. And again, that 50 million year growth time is sort of going on this slope or this slope. And as I said, the simplest path to preserve something close to Eddington is to start your collapse with a very, or start your black hole accretion, I should say, with a very massive object. So in this picture that Avi and Volker have promoted with the Lyman-Werner photons associating the H2, that actually then leads logically to this idea that you could have a chain reaction of the creation of direct collapse black hole halos. Okay, in other words, if you formed some sources of Lyman-Werner photons, could be POP3 stars, early galaxies, and then those dissociate the H2, you may have large high mass halos that can collapse monolithically. If you form the black holes within them, you may get more Lyman-Werner photons coming out, and that may then initiate more nearby halos that have their H2 dissociated. So if it's really a chain reaction, then you can just say that the number being created is proportional to the number that exists at any time. And I'll show you some semi-analytic models which roughly get that kind of evolution. So ultimately, in this picture, you're growing the number of DCBH halos. You're getting positive feedback from the fact that each one may create a black hole and give you back more Lyman-Warner photons. But there will be negative feedback too. The expansion of the universe will drive these halos apart from each other, so they're less likely to influence each other. Metal enrichment will be going on from galaxies that are also forming. And ultimately, this is key, ultimately you may photoevaporate away the halo remnant and stop the accretion. So there can be a time when this process comes to a stop. So if you take the simple ingredients here of rapid growth of the halos that form the DCBH, and ultimately a kind of sudden stop, a time at which you have so much photoevaporation that you stop the production, that's consistent with these semi-analytic models of Yue et al. And Dijkstra et al. This figure is from Dijkstra et al., which shows the growth of the number of DCBH halos versus time, or redshift on top. And in both cases, I'll mention the difference in a moment, in both cases you have a rapid growth era and then the numbers flatten out. So the rate of production is suddenly dropping at about redshift 12 or 13. Before that, you had this chain reaction process going on, and that you can get different growth rates with different models. There's uncertainty about exactly how much flux of these Lyman-Warner photons you need to dissociate all of the H2. So models do vary a lot in the predicted number per co-moving cubic megaparsec. And we're actually not modeling the number in this case. We're trying to understand the shape of distributions. Okay? So we're more concerned about this slope. And we're going to take for the numbers I'll show you later, we'll use the canonical model of Dijkstra et al., which is the blue line. Okay, so let's start putting our ingredients together. So this is a simple-minded talk. We're going to keep it simple. We have initial distribution of the seeds. That's an important ingredient. Essentially, the black holes will generally be forming from the collapse of short-lived supermassive stars. They tend to collapse into black holes when they get to about 10 to the 5 solar masses. But you can do more complicated modeling with a lot of effects, as Ferrara et al. Did. And they indeed find that the supermassive star collapse masses are peaked at about 10 to the 5 solar masses with some distribution. So we're going to take this as a log normal, which it is approximately. And the mean is 5.1 solar masses. So in terms of ln, it's 11.7. We'll adopt a standard deviation of 1, which is about what you have here. And as you may know, interestingly, for some reason, most phenomena in nature that are log normal tend to have a sigma somewhere between 0.5 and 1. It's hard to get away from that, in my experience. Okay, so let's add the ingredients together. If we have Eddington limited growth, and we'll allow this to even be slightly super Eddington as needed, and the number, so this is the growth rate of each individual black hole seed as it comes into being. For all later times, they're growing according to this formula. So that should be a T prime. Okay, so on the other hand, the number density of the direct collapse black hole halos is growing with time as an exponential because of that chain reaction process where they kind of dissociate H2 in the neighboring halos. So if that's the growth formula, this is the time since the Big Bang, that's T, starting from some T0, which is not the Big Bang. That will lead to a distribution of accretion lifetimes, T prime. That's not the same as T. T prime is the distribution of a lifetime that a black hole seed is accreting. That will be essentially a decaying exponential. If you're growing the number of objects over time, then you suddenly stop. At the time you stop, most of the objects have just been formed recently and they've grown a short time, but there's an exponentially decaying tail of objects that have been accreting for longer. So this is a decaying exponential with the appropriate normalization to make it a probability distribution function. And then what? So let's put all these ingredients together. If we have a log normal distribution of seeds to begin with, and all the seeds grew at the same rate, you'd simply shift the log normal. If, on the other hand, you have a distribution of times, you have to do this integral with the probability distribution. And let me get to the bottom line quickly, since I don't have time. If you have an initial log normal, if you grow for a short time, you move the log normal. If you grow longer, you get a power law. If you grow even longer, you get a power law that's truncated. The truncation comes into effect because there is that capital T finite time over which these black holes are being created before the photoevaporation of the halo sets in. But before that sets in, you get a power law tail, which is simply the dimensionless ratio of the growth rate of numbers divided by the growth rate of mass of each individual object. And you can predict where that tapering occurs. It's essentially the initial mean plus beta. Beta is your second important dimensionless parameter, alpha being first. Beta is the number of growth times you can fit in to that capital T time that you have for creating all these objects. Okay, so we can fit a quasar luminosity function. We've done this in the paper with my PhD student Arpan Das, who's right here with me today. So we took a bolometric luminosity distribution from Hopkins et al., which is Z equals 3. Z, sorry, my Canadian. I'm actually American, but I teach classes in Canada for so long. Okay, so so there we go. So you can actually get the tapering. You can get the power law and the tapering, and you can do a best fit. But what I'm going to point out is this not just a mathematical fit. These numbers mean something. And the more standard thing is to do a double power law fit, but we're claiming it's actually a tapered power law. This is the power law, which has a slope that is the physical ratio of those two processes. And the truncation is due to the fact that you ran out of time to create these black holes. And so the numbers kind of work out. With these numbers, the fact is any arbitrary pair would not agree with the model because both alpha and beta contain the growth rate of the masses. You are not free to let these two be completely independent numbers. If that was your best fit to your data, then this model would not be applicable. But if we do take, if this best fit, though, is consistent with the kind of numbers you get out of the semi-analytic model of Dijkstra with a lambda of about 28 per gigayear, the duration, 150 million years, those do seem to be consistent with these numbers for this particular data set. If you take a Eddington factor of about 3, I will claim that in theoretical astrophysics, 3 is probably close enough to 1. So there is some consistency of something Eddington or close to Eddington that fits with roughly 150 million years of formation and some kind of rapid growth of the DCBH halos. Okay, thank you. Yes. That's right. Yes, yes. I think LISA ultimately is free of all the conversion issues of going from mass to luminosity, which I just slyly put in there, assuming Eddington luminosity. Yes, I think that is the ultimate way to get the number density pinned down more accurately, and also the shape. This model, as I said, doesn't actually rely on a particular number density. So one would, in a way, hopefully work backward in the other sense if we can get constraints on the number density from LISA or other means.